Hello. In this video, we shall be discussing about the application of the balanced condition of the Wheatstone's bridge. Now, in the previous video in the series of current electricity, we had already obtained the balanced condition for the Wheatstone's bridge. The Wheatstone's bridge, somewhat the structure is like this. Uh, we are to study the application of the balanced condition of Wheatstone's bridge. Now, how does this balanced condition help us? Uh, as I had already mentioned, that we'll be using the balanced condition to determine the value of the unknown resistance or even the resistivity of a given resistance, or resistivity of the material of a given resistance wire in the meter bridge. Now, let me first draw the circuit for the Wheatstone's bridge, and then we'll be looking at how it's getting converted to or how is it uh, setting itself in case of a meter bridge. Now, this is essentially what the Wheatstone's bridge circuit looks like. It has a certain resistance. Now, if let us say this resistance is R, which is a known resistance, and here just for a change, as opposed to the just for change, as I had considered a known resistance over there, but now I am taking the resistance to be an unknown one, which is to be determined, and that unknown resistance is X, suppose. And here, let me take this as R1, the first resistance R1, and then here I have R2, here I have, say, R3, and as per the balanced condition, what we have is obviously there's a galvanometer bridging circuit or bridging wire comprising of the galvanometer, and then we have the rest of the circuit providing the source providing the energy, potential energy, to the circuit. And from that, what we have is, for a balanced condition, when there is no deflection in the galvanometer under this balanced condition, what we have is R1 divided by R2 is equal to X divided by R3. So knowing, in order to know X, what we have is the other three values must be known, that is R1 divided by R2, R3 gets cross multiplied, and that is how we obtain the value of X. Now consider a meter bridge. Now a meter bridge is simply a bridging circuit just like the above, but the length is 1 meter, that is 100 centimeters. We have a scale to measure the entire length. This is more or less the circuit diagram for the meter bridge. Now it has a gap over here, it's called as the left gap on the left hand side, and then it has a right gap over here where we may put the wire whose resistance is to be obtained, or even its resistivity for other purposes. Now here is a known resistance, which is obviously selected from a resistance box provided to the circuit, and then we have two end points over here. Let me take them as the end points, those points that I've marked over there, and uh, I'll be naming them shortly. Now this is a wire which is running in the just below that, and this wire has a length of 1 meter. This wire, so let me just name them now. So let these points be A and B. These points are C and D, where CD is obviously 100 centimeters, meaning 1 meter, which is the length of the circuit, 1 meter length. It has a scale graduations aligned with this wire CD, so that we can measure the length. Now, how do we measure the length? Where is the bridging part of it? Now, this center part over here consists of a bridging wire, which obviously is connected to the galvanometer, and from that we have a pointer which is known as a jockey, which is uh, brought, or which is put over that wire. What happens is that now this wire, obviously CD, that is the wire that has that is made of some material with some resistivity rho, and it has a certain length. Obviously, as you can see, the length over here is 1 meters. Now, going back to the previous circuit over here, how do we compare these two circuits? Now, the points, I will be just comparing them by the points that I have named. Let me name this point as O, let me name this point as J, which is actually in that above diagram. We have this point as O and this point as J, and the other 2 points being here the length, here the point is A, and here the point is B, the other 2 points. Now, the A and C segment that we see over here, they are just they just remain uh, at the same point. In this case, in case of the in case of the Wheatstone's bridge that we see over there, so does the so is the case with the points B and D on the other end. Now, the circuit, if you compare, this is one resistance, this is the unknown resistance. Now, in order to have this balanced condition that we have over here, in order to obtain that value of X, what we need is 2 other resistances. Now, the 2 other resistances are actually over here, this and this. Now, these two, if I as per the above figure, if I name this as R1, I name these 2 segments which are separated by the point J. J is the point where we put the pointer or the jockey, where we have obtained the zero deflection of the galvanometer. And when do we have the zero deflection? The zero deflection is the case where we have achieved a null point. That means we have obtained the balanced condition. So under balanced condition, what we have is that this meter bridge, the pointer is struck at different points on the wire, such that the galvanometer shows no deflection. Now, obviously, I've forgotten a major thing, is that I haven't connected it to the circuit, so that doesn't really make sense, does it? So the points A and B, just like over here, are connected to a potential source. The potential source is given over here, which is connected to the points A and B, and the circuit is complete. Now, the jockey is touched at different points over that wire CD, and wherever we achieve the zero deflection or the null point, or in case of the galvanometer, we say that that is the balancing point, or that is where the system remains balanced. The load is evenly placed on either side, and as a result of that, there is no current flowing through the galvanometer, therefore it shows no deflection. So this is R3 and R4 that sorry, this is R2 and R3 as per the above diagram that we have obtained. Now R2 is this, what we do is that we have the value of this length. R2 will be of a certain length L. Let me write that in another ink for you to identify properly. R2 is of some length, suppose L, and the rest of the length is obviously 100 minus L because the total length is 100 centimeters. Now, so what is the value of R2? R2 is simply equal to rho, that is the resistivity of that given wire. Let me write that a little below. R2 is equal to rho times of that length that we have obtained over there divided by A, area of cross section of that wire CD. And what is R3? R3 is obviously rho multiplied with 100 minus L divided by A. Now what we have finally over here is that X, that is the formula that we have written over here, X has to be equal to then R1 divided by R2 multiplied with R3. Now we have a known value for R1 because we have used a resistance box to put that value, and for R2 what we have is that R2 is equal to rho L by A. We need not be concerned about the rho and the A because that is the same in case of R3 that we write over here as per that formula above. And as you can see, the rho's and the A's can get cancelled out, and all that we are left with, I'm writing it onto the left side, all that we are left with is the value of X being equal to R1, that is the known resistance that is provided by the resistance box, multiplied with 100 minus L divided by L. So what you just need to know is the value of L, which is obviously obtained from the graduations that is provided by a meter scale which is connected to the arrangement over here. The meter bridge has a meter scale which is just connected to the board having that meter bridge, and those graduations help you determine this value of L. And from that L what you can obtain is 100 minus L as well, and from that you can obtain this value of the unknown resistance. Now you can use a screw gauge and to determine the area of cross section of the unknown wire over here, that is X. And from that, if you know the thickness of the or the area of cross section of the unknown wire, let it be suppose small a as I write over here, so X will be some resistivity rho dash, some different resistivity maybe, rho dash into its length is supposedly L dash divided by A being its area of cross section. So from that, with these known values and this value obtained from this meter bridge, you can obtain the resistivity of X, and that is how you obtain the resistivity of a given wire. So this is how we use the balanced condition of the Wheatstone's bridge in order to determine an unknown resistance, and the device which helps us to do that efficiently is the meter bridge. In most of the practicals you have these kind of setups where you have to obtain X. Now you can also verify the laws of combination of resistances like that of parallel combination and series combination. All you need to do is connect the wires having unknown resistance onto the gap provided. See, if the unknown resistance suppose was connected onto the left side of the gap that is provided, and the known resistance R1 is provided onto the right gap, so the conditions just change accordingly. Now if the meter bridge has X onto the left gap, and here's the galvanometer, and you have the known resistance, suppose R1 again, onto the right gap, and here the circuit completed, right? And in this case what you have is, if the length over here is just L, so this is 100 minus L. Now the conditions just reverse in this case, because with the resistance, unknown resistance onto the left hand side, what we have is X divided by L. I can simply write it as L instead of resistance, because resistance is directly proportional to the length, uh, is equal to R1 divided by 100 minus L. So now what you have is X to be equal to R1 into L divided by 100 minus L. Now what you can do over here is that you can you know take the taking the L, obviously you always count the length from the left hand side, okay. Although the readings on those on that scale that is provided to you has counting from both the sides, you can be able to count both the sides. If you are taking the left hand side as the length L, then the right hand side is 100 minus L. And if you are taking the counting of the graduations from the right hand side, counting it from 0 to from the right hand side, which is quite unusual, but if you can do that, then the other length is obviously 100 minus L. So accordingly the formula is just uh, it's not a fixed formula, it's just a formula which is obtained out of the uh, values that is obtained from these readings. So you need not be too worried about it. The formulas uh, are just created out of you know the observations. So you can choose any length as L, any length as 100 minus L, that doesn't really matter, okay. All that matters is that you take the proper balanced condition, that is the balanced condition, as I said in the Wheatstone's bridge, you can take it like this, that is the this ratio divided by this ratio, or the other way around, you can take this ratio horizontal divided by this horizontal ratio. Obviously the result is exactly the same. All you need to know is the value of the unknown resistance. Now that is the case of meter bridge. In the next video we'll be discussing about the potentiometer, and that will probably end the uh, current electricity part. It has another simple short uh, short portion related to heating effect of electric current, which we have already we already know the formula for power that is generated across a circuit, that is I into V. This is school stuff, but still if time permits, then we can definitely go for the heating effect of electric current. But that is for the upcoming videos. Till then, thank you for watching.